Hello everyone, welcome to topic 7 in our course Artificial Intelligence Concepts, Challenges and Opportunities. We are still in theme 2 where we introduce some fundamentals of the topic of AI and machine learning. Topic 7 is machine learning techniques. So we are going today to introduce a few concepts of machine learning. So the outline of the lecture will be machine learning techniques and supervised learning and regression process, learning with the training process, learning of classification problems, neural networks, unsupervised learning and reinforcement learning. We have already seen this picture or this figure in the previous topic, where we introduced that we said what kind of classes that we have in machine learning. So we said that we have unsupervised learning, where we don't have labels and we try to just make learning based on the finding and hidden similarity between data, and then we cluster them into islands, for example. Then we have semi-supervised learning, where we might have a few or portion of data that has labeled, or we have some information about the statistical behavior of data. Supervised learning, where we have labels of data. These labels can be numeric or classes. If it is numeric, then we call it regression. If it is classes like class A, class B, if for example expensive, non-expensive, healthy or non-healthy, faulty or non-faulty, spam or non-spam. So we have some kind of classes, and when you call them classification. And finally we have the reinforcement learning, where we don't have teacher, but we have like a critic, where we say that it is good or bad action of the intelligent agent. We are going to explain this in some detail in this lecture. Okay, so we explained this already. So we let us start with the supervised learning, and mainly with the regression. So in the regression, as I said, we have a numeric, but in the classification we have classes. But we have already attributes or data, previous data, recorded data, database that we have already, and we like to learn from them. Okay, let us start with a simple example, and maybe I can open like note here to write to explain these important issues. Okay, we have too many examples that we can think about, but let us start with maybe one of the hot topics today is the batteries. So we know today that we have a battery, like very large size batteries used for many applications, like storing energy for electrical cars and so on. So for example, when you have solar cell panels, then you can store the energy in these batteries. Also, when you have extra generated energy from wind turbine, then you can store them in these batteries, and then to reuse them later, or as we said, in Tesla car and many new electrical cars. Based on that, the states of the battery is very, very important. So we need all the time to monitor the state of the battery, the health of the battery. We don't want suddenly that the battery might explode, or might go into fault, so it suddenly stop working and so on. Okay, so if we assume that, okay, we have the battery here, and we have some kind of previous measurements or previous data that we have. So what kind of data that I am not expert in batteries, but I just guess. So I might say that we have the battery, maybe we start with the manufacturer of the battery. Okay, the manufacturer, maybe we have higher reputation manufacturer, and we might have like less reputation one, and we might have for example the cycles, the number of cycles means that charging and discharging, charging and discharging. So that how many times that we have this cycle of charge and discharge. It of course it affects the health and the age of battery, and maybe a manufacturing date. So when it was manufactured. So even sometimes you buy a new battery from the market, for example, but when you check it, you find that it was manufactured like 5 or 6 years ago. So this will affect the age of the battery. and also the kind of battery, maybe kind of battery. So it means that we know that we have different technologies in the battery. So what is the kind of this battery? So I think it should be important. Maybe the internal discharge, it depends on the internal impedance, so internal discharge of the battery discharge. So it means that if your battery is not connected to anything, so we have some kind of discharging internally, and then you can measure it. So somehow that you don't connect the battery to anything, then you after some time you find what is the capacity of the battery, then you can estimate that internal discharge. Maybe operation temperature, so the temperature when it is working in normal condition, what is the temperature of the battery? It might be somehow related to the internal impedance, and this could also be like indication for the age of the battery. As I said, I am not expert in batteries, so I am just guessing about what are the possible that parameters or attributes that might affect the age, and so on. So you might have even more parameters, and at the end we have the age of the battery. The age means that the age here, we define it from the time when it start in operation until the time it is like done, so it cannot be used anymore. Okay, then based on these data, so we have data here, and then we have the age. For example, this one has been working for let's say 65 months, and this one was working for like maybe 60.05 months, and so on. So you have data here, you have data, and this is called the attributes, and this is called the age is our interested outcome. So now what we can do, if we can build some algorithm that it learned this data. It learned this data. What is the good thing of this algorithm? The good thing with this algorithm, that based on some measurements, even the battery now is working with very good, in good condition, but when we put these attributes to this algorithm, it can give us some expectation of the age of this battery. For example, they tell us that under this operation condition, this battery, the age should be, let's say, 70 months. And now we are at 65 months. Then we know that we still have on order of 5 months about before we lose this battery, so we can prepare, or we can change the operation condition of this battery, or we can prepare to replace it. So this algorithm now learned this data. Okay, so it is very important that it learn the data, not memorize the data. We are going to explain this in detail soon. So now if we build this algorithm, we call this as like supervised learning. Why supervised? Because we have a teacher already. We have the history, so we have teacher. So the teacher tells us what will be the output based on the previous database that we have. Okay, and this process is called regression. This process is called regression. Now, if we don't have, if we are not interested in the exact age, but maybe instead of exact age, we might have like another output. So the output is called that we have these attributes. Then the output that we like to see based on the previous, that this battery is healthy battery, good battery. This one is non-healthy, not healthy, healthy, not healthy. So now we don't have, the output is not a numeric, the output is a class. So is it healthy or non-healthy? Okay, so now we have a classification. We like to classify it. Now the algorithm is called the classification, not regression. The previous, when it is a numeric, we call it regression. That when the output is classes, we call it a classification algorithm. Okay, so I hope this is clear now, and we can now continue the slides. Okay. This is actually what we are doing about the regression process. So we have the system, whatever was the system, the battery or the data. So we have the input. The input actually is the attributes that we have, or the inputs. Okay, and then the outputs is dependent on what we are looking for. What we are looking for. And then the system here depends means data. Remember that, as we explained before, it is a data-driven system. So we have already data before, and we try to exploit the available databases. Nowadays, there are some like factories, there are some like societies, they have like huge data, maybe in digital format or even in papers. So we like to build a system based on this data, and we like to have this learned algorithm. So it can be regression, it can be classification model, and we have the input. We put the input to the system, and we know the output of the system and compare it with the output of the model, and the difference is the error. The error is the difference between the actual output and the output of the model. Then we can take this error and we can update the parameters of this model in order that the model will match the system itself. So it is some kind of system identification. If some of the attendees in this course, they have control engineering or electrical engineering, they should know what is system identification. So actually regression is just some kind of system identification where this one will represent the actual system. The problem here that whatever that input, that the actual input or the real input, actually we don't know. Even the data that we have, what we have, actually it might be, for example, distorted before, or it can be biased. Some of data could be missing, and some data already can be recorded, would be that recorded wrongly. So maybe during the for this battery example, we have this database, the database of the battery. Maybe the engineer who entered the battery, for example, age, or the battery like for example internal resistance or internal impedance, maybe they bought it wrongly by mistake or intentionally, or maybe the device that it was used for measurements, it has some fault. So all the time we might have faulty data. So we should remember this during the process. Okay, so we shouldn't be sure 100% that everything should work from the first try. So and now we call this in the model distortion, or we may have noise, and then the data comes also to the regression model, and the output also that the measurement that we measure, the output, it can be also distorted, it can be noisy as well. So for example, in the battery example, we say that it is the age, our output is age. So the age is measured by the person that who study or monitor the health of the battery. So when the battery is faulty, then he or she wrote in the system what was the age of this battery. So there might be some mistake in when we bought it, or it can be also some biasing. So maybe someone they don't like this kind of battery, so they put the age less than the real number, for example. So it is intentional. So it is biased intentionally. So or it can be by mistake. It can be any error happen. So this could also be represented by distortion and noise. So this is the concept of regression in general. So regression actually is not only for machine learning. Regression is very well known for many decades, and is applied, as I said, in different applications. System identification, when we deal with one input and one output, we call it in numerical analysis curve fitting. So curve fitting is actually very similar to the regression, but it is one dimensional. Okay, so now we have in the regression, assume that we have this data. Okay, so we have this measurements, and in these measurements, so we have available measurement. It is given like stars. Okay, as you can see them, and now we like to find or we believe, for example, that the best relation between input and output is linear. So it is just a line. Okay? So we are looking for what is the best line that it can represent these data. Okay, what is the best line which can represent this data? You can see here the difference between this input and the line is called, for example, error 1. Here it is error 2. Here is error 3. Here is error 4. And here is error 5, error 6, error 7, and so on. Okay, it is apparently that we cannot make the error that 0, because we have the data is between both sides of the line. So we like to find the best position of the line, or the best equation. This line could be represented if we call this, for example, as x and this is as y. So we can say that a equal to ax plus b. So we are interested to find what is the optimum a and optimum b in order to minimize the total of the square root, or the square of the error. So we are looking for the total of some kind of measure of the length of the error. So one way that we can say that from I equal to 1, here we have, for example, 7, up to 7, for example, the error I square, or we can take the absolute value of the error I. And the idea here is we should remove the negative sign to have a real measure of the error. Otherwise, if this error is positive and this error is negative, so they can cancel each other, and it doesn't mean that there is no error. There is already error, so we have to take the absolute value or the square of the error. Anyhow, so now we can find the optimum or the best line. So this will be the best line. Now we have a non-measured data or not available data. It was given with these circles. So actually we can usually apply this line for a data that it was not shown during the learning or during the regression. So it should work. So if the data that we are looking for we are measuring is between the data that we have, we call them interpolation. If we check the outside this band, for example, or within this x, then we call it extrapolation. So we can use it for interpolation or extrapolation, prediction, for example, or forecasting. Okay, the good model, the model which could be used in between for interpolation and as well as extrapolation. So if your model that you build model, it was able to exactly, or not exactly, but it was very good accuracy, with very good accuracy that they can predict the output for inputs that were not shown during the learning process, and it can be done for interpolation as well as for forecasting. For extrapolation, it works very good in any condition. It means that your algorithm has learned very well the problem under study. Otherwise, of course, we might have some kind of problems. So in the red line here, or the red curve, we have another kind of model. So maybe you are not happy with the linear model, so you can also find some non-linear model to catch the relation. Always in models we need to trade off between accuracy and complexity. Some models, they can be very complex. So complex models means that it will need a lot of computation, for example, and the accuracy also is very tricky term. Actually, accuracy with what? It is important, not accuracy with the data under learning, as I am going to explain now. We are looking for accuracy for the data, high accuracy for data which was not shown during the learning process. We are looking for generalization, not memorization. We are not at all interested in to memorize the data or the database. The database is already there. We have already the database in our computer, so we are not interested to build algorithm to memorize the data. The data is already there. We are interested to build algorithm to learn the data, not to memorize the data. So this is important, and I'm going to explain what is the difference between them. In general rule, more data means better modeling. In general way, of course, it's not for any more data. It should be more data which has information, extra information, not repetition of some data. The data should span the problem very well. Otherwise, it might mislead the learning process, as we can see here. For example, if we are interested to learn this relation, of course, we are not usually dealing with practical problems, not with this nice shapes, but just to explain. So assume that you have this data, that this red dots is the data available, but the real process is sine wave. Okay, now we use this learning data for the learning process, and then the process or the output, it gives you the best algorithm to represent this data is just a line like this going to infinity and here going to minus infinity. Of course, the result is completely wrong. Okay, but we don't claim here, we don't blame the learning process or the learning algorithm. Here we blame data. The data was not spanning the problem very well. So it showed only portion of the problem, not the whole problem. Okay. Now we talk about very important issue in machine learning that we try to avoid is the overfitting. Overfitting or memorization problem. The overfitting means that you build algorithm, it is complex enough to be accurate 100% or 99.9% accurate with the training data. During the training data, it works perfectly. But when you try them with data, new data, it fails. So we call this problem as overfitting or memorization problem. Let me give this simple example. Assume that this is the hidden relation between output and input. We don't know this relation. Assume that we don't know it. It is unknown for us. And we are interested to build algorithm or a regression algorithm in order to catch the relation between input and output. Okay? It is very simple example, of course. In reality, things are much more complicated. We have always uncertainties in realities. Okay, now we have, this is the learning data that we have. 1 gives us 1, okay? And 2 0, it gives us 1. And you can try them, they are correct. You can see 1 plus 1 is equal to 2. 1 plus 1 square is equal to 2. Minus 1 equal to 1. 2, 0, it will be 2 plus 0 minus 1, it will be 1, and so on. So we have this. This is the data that you have. You came to some regression algorithm and you give this data and you make the learning because you know the input and the desired output. This is the desired output and this is the input. The desired output here works as teacher. The desired output here works as teacher. So we teach the regression algorithm this relation. Now you have two different regression algorithm. This regression algorithm it is one example for memorization and this one example for generalization. Of course, depending on how complex. So sometimes you use very complex regression algorithm is not needed to use complex or high order algorithm, which is not needed for the problem. So what happened now? When we put 1, it gives us 1. So it is 100% correct. When we put 2, 0, it gives us 1. It is 100% correct. Now we give 3, 2, it gives us 6. It is 100% correct. We put minus 1, 3, it gives us 7. It is 100% correct. So when we put the same data, it gives us exactly the same result. Is that okay? No, because we have already the data. So it is not. I am not interested in this portion of the testing. I am interested if I bought another kind of data. So if I bought some kind, like some input which was not given before, like 0, 1. 0, 1 here is not exist. Okay, is not existing. So if I put 0, 1, okay, let us check. 0, 1, 0 plus 1 is equal to 1. 1 minus 1 equal to 0. So the result should be 0. But here it gives us 4. When I put 2, 2, 2 plus 2 square, 2 squared is 4, 4 plus 2 is equal to 6, 6 minus 1 equal to 5. So result should be 5. Here it gives 18. Okay, so minus 10 and 4, it gives us 29. How much it should be? Minus 10 plus 4 squared is 16. 16 minus 10 is equal to 6. 6 minus 1 is equal to 5. Here it gives us 29. So we call this machine learning, or this algorithm that for regression failed. It is not good. It is not good. Even it gives us exactly the same result during for the training data, but during the testing it gives bad result. So we are not interested in such kind of data at all, of such kind of result. Okay, now look to the second one in this generalization. When we put 1, it gives us 1.3. Actually, it is not the same as our result, the learning result. It is close, but it is not 100% correct. 2, 0, it gives 0.8. It should be 1. So it is not exact. 3, 2 gives us 5.2. It should be 6, and so on. But when we come to the testing data, which was not shown to the algorithm, 0, 1, it gives 0.2. It should be 0, but 0.2 is close to 0. 2, 2, for example, it should give us, like we said, like give us 4. Here it gives 3.1. Okay, it is not very close, but acceptable. 4.9. It should be 5, but here it is 4.9. It is quite close. So now we think that this regression, maybe it is not excellent accuracy, not very good accuracy, but still it works. So the regression algorithm start to capture the real relation between the input and the output. Remember that in real application, it is not possible to have exact results due to noise, due to distortion, due to many different kind of problems in the training process. So higher model or higher order model doesn't necessarily mean better accuracy. Okay, so now assume that we have the actual model, or the real model, is given by this red curve that you have seen. So this is the data we have. You can see this is the data that we have. Now we have two models. The model 1, with the model 1, you can see that you have 0 error at the data. You have 0 error at the data, but it is bad model. It is overfitting. This is the word of overfitting came. You can see that it is overfitting. It memorized the data. But in model 2, it has some error with the measurement, but still it is much closer than to the real problem than this model 1. So model 2 is better than model 1. Even model 1 gives us 0 at the measurement point or at the training point. But we are looking for generalization, not for memorization. Okay? So in overfitting, we have very small error in the training data, can be 0, very small bias, large error variance. It fails when applied to data that was not part of the training. Reason for overfitting: unnecessarily complex model. So we use, for example, the relation is linear, and you use for order problem or for your order fitting, for example, and a very complex, unnecessarily complex model can cause this overfitting, and also it can be due to like small or not enough data set. So when we have small data set which is not enough to capture the relation, it can be also due to the many times of training. So because of the training, as we will see, that we repeat the data many times. So sometimes it is good to stop at certain time, even you didn't reach to the minimum possible error, because you are not interested in the overfitting problem. Okay, underfitting is similar to the overfitting, but in the reverse direction. It is also causes like bad result for the testing data, for the data, even for the training data. And the reason here actually due to the model complexity is lower than the actual complexity. For example, you have data like this one. If we assume that it is only two-dimensional data, x and y, so we have data like this. And then like scattered data, and I want to find the best line to fit this data. Of course, we can find the best line, but the best line, it is clearly that it is underfitting the data, underfitting the data. So we will have error not only for the training and not only for the testing or for the validation data, but also for the training data. Okay, and also the data is not good. Either in size, small size data, which is not spanning all the problem, or the quality of data due to noise, due to biasing. So there are a lot of problems that may cause the underfitting. So remember that we are not we should avoid during the training, we should avoid underfitting as well as overfitting. How to manage this? So I will give it very fast, and then we in this part or this clip. So actually we divide our data into 3 parts. The first part is called learning or training data. In the learning or training data is the part where we make it the training process, and the second is the validation set. So once you have data, you have already the database, okay, the database. Let us that you have 1000 entry for the database. You don't use all of them for the training. No, you can divide them like 50-50, 50%, 50%. So you can use, for example, 500 for the training and then 500 for the validation. So the validation is very important to check if our algorithm captured the real relation or it is just overfitting or underfitting. Okay, and then the testing set. So the testing set, actually, once the data has been trained completely, then it goes to the work, and then we can monitor it, how it behave in the testing phase. But during the training phase, we divide the data into training set and validation set. So this is very important process during the learning in order to avoid the overfitting or the underfitting. So we have, or in order to find the optimum size of the regression algorithm, we have to be careful how to divide the data into for the training and validation. Usually we have several kind of dividing the data. It can be, for example, 80% for the training, 20% for the validation, or 50% for the training, 50% for the validation, 70% for the training, 30% for the validation. Depends on many things. Depends on the size of data, depends on the type of data itself, type of the problem, the complexity of the problem. But remember, here we have always that very important, and it is a rule of thumb here, that during the training, the experts in the machine learning, they know that we can build our experience based on trial and error. So you have the database, you have them already, you have your regression algorithm. You start, for example, with 50-50, you can increase to 60-40, 70-30, and you can play with data. What kind of data that you show is data, what is the data quality? It is always important to clean data, because some data has a lot of redundancy, so repeating data usually is not counted. So if you have data and it is repeated, for example, if you have data like 1, 2, 3, and then you have 2, 4, 6, so actually this second data is just 2 multiplied by the first row, so this one doesn't have information. It is just linear repetition of the first one. So whatever number of data, such kind of data is not useful, so it is enough to have only one of them. So how to remove this highly redundant data and so on. So they are quite important in machine learning. The learning process actually it goes in this way. So this is the average error during the learning process. So during the learning, with the algorithm complexity, so as you increase the complexity, the training data, during the training, the error is going down and down and down, and it can when the complexity is large enough, then you can have even average 0 error. You can reach to 0 error for the training data. Is this good? Unfortunately, no. This one is not good at all, because it means that you most likely that you have memorized the data. You didn't generalize the relation between input and output, but you memorize them, and also you may learn the noise in the data, that we are not interested to learn noise in the data or distortion and so on. So we are interested to learn the relation, the actual relation, the map between the input and the output, not to memorize the set of data that we have. Okay, but if we look to the validation process, so now we have certain, so we make the learning. For example, we are here, so this is the complexity of our algorithm. We got this training error, we check that, then we make the validation. In the validation, of course, we don't make a training, we just take the left part from the training data. As we said that we have, let's say we have 100 input data, then we use 70 for training, and then the rest 30 we use them for validation. Then I use the rest 30 here. I found this error, I increase the complexity, then I measure the validation error, I increase the complexity, I measured the complexity, the validation error increased here. This is the validation error, and then we come here, this is the error. So we have this validation error, then I increase the capacity, I found that the validation error start to increase, and if I increase, the validation error is increasing. What does that mean? It means that I start to have overfitting. I started to have memorization effect. Then I should go back to this point. This point is the minimum. This point is the optimum. You cannot do better than this. Based on the data that you have, you cannot do better than this one. Of course, I assume here that the data went already through the cleaning of the data, and this is the best data that you can have. So based on the data, and you tried also different kind of percentage between the training and validation. So this is the best that you can achieve with this data. I hope this is important. This is actually very important. So I hope that you understand it. It is one of the key points in machine learning. Okay, let us stop here. So next part we will start with the quality of data sets and the impact of the quality on the training and the quality or the efficiency of the obtained machine learning algorithm. Thank you very much. Bye.